Okay, so can you guys see my screen? Hello? Can I start?
Yeah, we can hear you. Go ahead.
Okay, great. Okay, now we can start. So first, hello everyone. Good morning. My name is Zidu Lin, and I am an MP3 fellow working at University of Tennessee and also University of New Hampshire. So first, I am very sorry that I cannot be here in person due to some weird visa issues. So as the penalty, I woke up at 3 a.m. these days to attend the workshop. But definitely worth it. And also, I am very happy to have this chance discussing with you guys about my current understanding of the joint analysis of the correct supernovae physics using both the neutrino and the gravitational wave signals. So in the next half an hour, there is probably just one question that we want to understand. So which is that what can we really learn about a real correct supernova by using realistic neutrino and gravitational wave signals? So, but before we start the talk, I would like to thank all my collaborators listed here, and their contributions to the projects are huge. So to make the talk more exciting, let's just imagine that there will be a correct supernova exploding in our galaxy tomorrow. So, but please don't blame me if that doesn't happen. But anyway, what's the first thing that we want to do if there is such a star? Of course, I mean, everyone knows that if there is such an exploding star, then there will be a lot of neutrinos emitted out from that star. And those neutrinos can be detected by our neutrino detectors. And thanks to the great improvement of our detectors, very likely we will be having tens of thousands of the neutrino events via our most robust neutrino detection channel, namely that inverse the beta decay channel. And that is already a very huge success. But is this the end of the story? So we still want to say something about that star based on the realistic data. So it's not the end, but it is just the very beginning of the story of our correct supernovae analysis. And there are a few naive facts when we are trying to understand a real correct supernova. The first fact is that different from the numerical simulation, the angular dependent neutrino emission as well as the motion of the correct supernovae matter, they cannot be directly observed. So what can only be observed are just those time and energy dependent neutrino events on different detectors via different neutrino reaction channels. And those neutrino events are having very different uncertainties due to very different nuclear physics about the neutrino nucleus reactions or the neutrino part or the neutrino nucleon reactions. So the question is that how can we reconstruct the features of a real correct supernova based on real events? So to answer this question, we need to understand what kind of the physics inside the star may have an influence on the observables, where there are a lot. So for example, from the microscopic nuclear physics side, we know that the finite temperature equations of the state, the exotic state of the correct supernovae matter, and those many-body corrections on neutrino-nucleon reactions, which is a subject I have been studied for so many years, and also those complicated neutrino flavor oscillations, and also some kind of the beyond standard model neutrino physics, all the things can have an influence on the neutrino signals. So from the macroscopic astrophysics side, we know that the mass, the compactness, the structure of the progenitor star, the proto-neutron star mass and the radius, maybe the rotation and the magnetic field of the correct supernovae, and also, of course, the distance and the viewing angle of the correct supernovae. This stuff can also influence the directly observed neutrino signals. And this is both good and bad. The good news is that this means that our neutrino signatures, that messengers, can potentially bring us a lot of information about a lot of different interesting physics inside the star. But the bad news is that there might be a degeneracy problem we may need to worry about, which means that given one set of the observable, we may have more than one candidate model that can explain it. So in my opinion, I think it might be necessary for us to at least have a rough understanding of that degeneracy problem before we can reliably reconstruct the picture of the cortex supernovae using the neutrinos. So the question is that what features of those neutrino signals may suffer a degeneracy problem? And what features of the neutrino signals may suffer less severe degeneracy problem? And as far as I know, probably there are no systematic study yet to the first question. But for the second question, my very naive estimate is that probably those oscillatory features on the neutrino signals may suffer less severe degeneracy problems simply because oscillation is such an informative phenomenon. By detecting the oscillation frequency, the starting time of the oscillation, and also the duration time of the oscillation, you can very effectively constrain your model and decrease the number of the candidates. But still, we want to understand how to break the degeneracy if there are any. So the simple answer to that is that maybe we can try to consider some kind of the joint analysis, for example, by combining the neutrino and the GW information. And that may very efficiently break the degeneracy. So in this talk, I will be focusing on the answer to the last two questions, but if we will have a little bit time, I can tell you guys my current understanding of the first question. So, okay, let's now begin the discussion about the oscillation. When we are talking about the oscillation, probably the first thing coming out from your mind is the so-called SASI phenomenon. The SASI is a macroscopic sloshing motion that has been observed by a lot of numerical simulation groups. And it is also believed that this type of the SASI phenomenon may have an influence on both the neutrino and the gravitational wave signals, simply because this macroscopic sloshing motion have a chance interacting with both the neutrino sphere and the surface of the protoneutron star. And indeed, in several numerical simulations, we do observe the modulation due to the SASI on both the GW and the neutrino signals. And in these works that we are going to discuss, we are doing a joint analysis about the SASI based on the numerical simulation done by Kuroda and Keiko Taki. Very nice numerical simulation works. When we are trying to understand the cortex supernovae by using a joint analysis, actually, we are just like a group of blind people that is trying to understand what is sitting in front of us by touching it. So the guy who is touching the nose of the elephant may think it is a snake. The guy who is touching the body of that elephant may think it is a wall. And only when those guys gather together and communicate well with each other, they may figure it out the right answer, which is that it is neither a wall nor a snake, but it's an elephant. And that is exactly the case of a joint analysis. So, okay, let's now go to the neutrino channel of that joint analysis. So here, the basic question is that how can we confirm the existence of the SASI based on realistic neutrino signals? And this seems to be a very naive problem if we think about the case in numerical simulations, because that is so obvious. If you have a numerical simulation with the SASI, then obviously these neutrino signals at late time begins to oscillate, and then you can very easily identify a model with the SASI. But that is not the case in the real world. So in reality, all those neutrino events detected in our detector are unavoidably fluctuating due to the statistical fluctuation. And as what we can see on the right-hand side, now it is no longer easy to identify which curve is coming from a model with the SASI and which one is coming from a model without the SASI. So the interesting thing that I want to mention that the noise of this neutrino signal is coming from the statistical fluctuation, which means that the noise is dependent on the signal itself. And that is different from the case in the GW. From the GW side, the noise is usually independent from the signal. And that makes it a little bit difficult for us to directly migrate an already mature data analysis method from the GW side to the neutrino side. And that motivates us to invent a new statistical tool to analyze this type of the oscillation phenomenon. And that tool is the so-called CCSNe. So the basic idea behind the CCSNe is pretty simple and naive. So the basic idea is that if you want to tell if an animal is an elephant or a giraffe just based on their height, then you don't need to create a very complicated template that can reproduce the weight, the color, the smell of the elephant and the giraffe. So what you need is just a ruler that can quantify the height of that object. Given the ruler, you can already measure the height of the elephant and the giraffe separately, and you already have a quantified value that you can compare with. And then based on that, you can already tell what is standing in front of you. So coming back to the CCSNe, similar. So here, the ruler here, in this case, is our so-called CCSNe, which is a very simplified neutrino time series template that only features the oscillation behavior. So by having this kind of the CCSNe as the ruler, you can compare it with the realistic neutrino signals either with or without the CCSNe. And when you are comparing the CCSNe with the realistic neutrino signals, what you can do is to calculate this CCSNe quantity, which is a likelihood ratio. So on the numerator, this is the likelihood that the realistic neutrino power spectrum can be realized by our CCSNe template with the oscillation. On the denominator, this is the likelihood ratio that a realistic neutrino power spectrum can be realized by a CCSNe template without the oscillation. So by having this kind of the construction, we can easily understand that if our realistic neutrino signals are oscillating because of the CCSNe, then this likelihood ratio value will rise up and vice versa. And by having something like this, we can quantify the oscillation behavior on the neutrino signals. So that is what is happening here. So on the upper three panels, so if we are using a realistic neutrino signal with the CCSNe, then what we have is a probability distribution of the CCSNe quantity illustrated by this red bump. But if we have a realistic neutrino without the CCSNe, then the PDF of the CCSNe quantity is illustrated by this blue bump. So we can see that at 1 kbc, these two bumps can be easily identified, but as the distances increases, you will see that the overlapping region of these two bumps are becoming larger and larger. And as a result, we will have worse and worse receiver operating curves. And that's how we are going to quantify the detectability of the CCSNe. And that's the basic idea of our neutrino channel analysis. And now we can go to the GW channel. So similar as the neutrino channel, we can define a GW CCSNe. And similar as what we have, we are doing this by following the same construction idea. So the GW CCSNe quantity is again a likelihood ratio, but the numerator here is the likelihood that a waveform, realistic waveform, can be realized by a gravitational wave model with the CCSNe. And in the denominator, this is the realistic waveform that can be realized by a model with pure noise. And that is how we are going to define the GW CCSNe. And again, we have the PDF of the GW CCSNe quantities illustrated by this red bump, and the GW CCSNe quantity probability distribution without the CCSNe illustrated by this blue bump. And when we have two probability density distributions in one dimensional, we can combine them. And then we have a two-dimensional map of the probability density distribution that can identify the CCSNe region. So the basic idea is that if you have such a 2D map, then you can already imagine that if your model doesn't have the CCSNe, then both the neutrino and the GW seismometer quantity will be low, so that the probability density distribution will now be locating at the left bottom corner here. But if you have the SASE, then you can imagine that the seismometer quantity from both the neutrino and the GW trino rises up, then this probability distribution is now locating in the middle of the panel. And because of the obvious difference about the location of that distribution, we can now propose some kind of the two-dimensional curves to identify the SASE region from the no SASE region. And of course, we have more than one choices to use as the SASE region threshold in a two-dimensional world. So for example, we can define the SASE region as the area inside this very large rectangle, or we can define the SASE region area as the region outside of this small rectangle. And similarly, we can say the SASE region is somewhere outside of this triangle or somewhere outside of a parabolic line. And just depends on the definition of your SASE threshold. We have different types of the receiver operating curves. So which is shown here. So the main information that I want to mention here is that these receiver operating curves have very different features at different distances. So at very low distances, what we see is that the neutrino messenger, which is somehow represented by this black dashed curve, which is here, it is dominating over the GW messenger, which is represented by that black dashed curve. And the joint analysis is usually lying in between. At very high distances, we see that the GW messenger is behaving much better than the neutrino messenger. And again, the joint analysis are lying up in between. And this can be easily understood because the magnitude or the strength of your GW messenger is proportional to 1 over the distance, but the strength of your neutrino messenger is proportional to 1 over the distance squared. So interesting things happens at 5 kbc. So at this type of the distance, the performance of the GW and the neutrino messenger are about the same, but when you combine them, you see that the joint analysis will give you an ROC curve that is behaving better than both the neutrino and the GW messenger alone. And that is where a joint analysis may play a role and may be better than a single messenger. So, okay, so that will be my end of the story of the SASE, but it is not the end of the story of the oscillation. Because there might be some other interesting physics can cause an oscillatory neutrino signals, such as the hadron-quark phase transition inside the star. So for example, recently, several numerical simulation groups has already seen that when you are considering the possibility of the hadron-quark phase transition, then what you will see is the second bounce of that compact star deep inside the quark supernovae. And after the second bounce, probably that proton compact star may begin to oscillate. And the oscillation of the density of that proton compact star may induce the oscillation of the neutrino signals. And this type of the neutrino signal is caused by the phase transition, but again, it's just an oscillation. So we can use the similar idea, just like the seismometer, to analyze this kind of the phase transition-induced oscillation, and we call it to be the PT meter. Although the name are different, the idea is the same. So we can use that to quantify the detectability of this PT-induced oscillation. We can also roughly extract the frequency, the starting time, and the duration of that type of the oscillation. And this information could be very useful because it helps us to understand the damping behavior of that kind of the proton compact star oscillation. And that damping is related to very interesting microscopic nuclear physics, which is the bulk viscosity of a hadron quark matter. So, okay, that's the final end of the oscillation story. So now, in the last several minutes, I would like to go back to the first problem, which is that what features of the quark supernovae signals may suffer a degeneracy problem. And in my very naive understanding and maybe even estimation, I think a lot of very fundamental neutrino features may suffer a degeneracy problem, such as the average energy of the neutrinos or the neutrino luminosities, simply because those features are so general so that they can be influenced by so many different physics. They can also be influenced by the approximations made in our neutrino transport equations in the numerical simulations. So the question is that how can we systematically understand the degeneracy problem when we are trying to do a model identification when there is a real cold-crack supernova exploding in the sky? So my current understanding is that probably that kind of the degeneracy problem can be attacked by using a Bayesian inference. So here we propose a new type of the Bayesian study where we are using a Gaussian mixture model serving as the prior. So what is a Gaussian mixture model? So in this type of the model, we are using a multidimensional Gaussian distribution to represent the neutrino fluence predicted by a lot of different numerical simulations. And then we can sum up these Gaussian distributions weighted by the model probability. And in this way, we will be having the prior distribution of the neutrino fluence that is required by a Bayesian inference. And this type of the prior distribution is almost all model agnostic. After having the prior, then what we can do is just to randomly draw neutrino fluence from the prior, and then we calculate the corresponding likelihood of that neutrino fluence given the experimental measurement and the uncertainties, and then we repeat it once and once again until we have a good sample of the data with good statistics, and that will be served as our posterior distribution. So the advantage of using a mixture model is that we not only have the posterior distribution of the neutrino fluence, we also have the posterior distribution of the model weights. And those model weights give us very interesting information about the degeneracy. For example, if in the posterior, we see a very sharp peak of that model weights, then it means that the observation can help us to break the degeneracy. So that's how we can use a Bayesian inference to attack this kind of the degeneracy problem. So here is a toy model. Very simple. Now I am only using two model predictions to make that mixture model. The first model is a successful explosion model with the progenitor mass being 15.01. The second one is a failed explosion model that collapsed to a black hole with the progenitor mass being 15 solar mass. After having these two models, we can then, for example, I forgot to say that I call the first model Model A and the second model Model B. So here in the left-hand side panel, I am using the data from the Model A to train my Gaussian process. And now my Gaussian process can be used to represent the neutrino fluence from that Model A. The Gaussian process distribution is illustrated by this red band, and we can see that it can well reproduce almost all the features of the data in Model A, which is illustrated by this green dashed line. And on the right-hand side, I am using the data from Model B. And again, I use that to train the Gaussian process. And again, this Gaussian process can well represent almost all the features of that neutrino fluence from Model B. And which means that this is a very flexible expression of our numerical simulations of the neutrino fluence. And after training these two Gaussian processes, I can then begin to make a mixture model, like which is represented by this equation. I can say that the model weights to be 1-to-1, and what comes out is this kind of the neutrino fluence probability distribution, which is lying in between the green and the blue curve, which is as what we expected. If I set the model weights to be 10-to-1, then it looks more like the neutrino fluence generated by Model A. If I set the weights to be 1-to-10, it looks more like the neutrino fluence generated by Model B. And that's how a mixture model may work. Okay, after constructing such kind of the mixture model, we use that as the prior distribution. And then we assume that we have a pseudo observation coming from the Model A. And this is the posterior distribution of the model weights. For example, the model weight for the Model A is now concentrating on the higher end. On the other hand, the model weight of the model B is now concentrating on the lower end because we now have some kind of the observations, pseudo observations coming from that successful model. So that's how this kind of the Bayesian model mixing can be used in the Bayesian inference, and that's how this type of the study can be used to understand the degeneracy problem, in my opinion. Okay, now I come to the conclusion, very simple. The first thing is that now we have an effective way that can analyze the oscillation features on the Kokai supernovae neutrino signals, and also we can combine them with the GW information, and the detectability of the SASE can be improved in a specific range of the Kokai supernovae distance. And finally, just my own opinion, probably the Bayesian inference can be used to understand statistically and systematically about the degeneracy problem. Of course, there are a lot of related questions about this kind of the Bayesian study of the Kokai supernovae models. For example, we still need to understand more about how to build the prior of our Bayesian inference. And also, we may even dream about an ultimate version of the Bayesian inference in which we have the GW information, neutrino information, and even electromagnetic information that come together as the Bayesian constraints to improve our posterior distribution of the Kokai supernovae models. That could be possible in the future, and I think that could be interesting. And yeah, that's the end of my talk. And at the very end, I thank all my collaborators, and also I thank all the guys listed here for the fruitful discussion. Thank you, everyone.
Thank you, Zidu. Wonderful talk. We have time for a couple of questions. Is there any question in the room? Okay, Olivia up there.
Hello, thank you so. Oh, is this on? Oh yeah. Thank you so much for the talk. I really appreciated it. It was really engaging, to be honest. You're a really good presenter. Um, what I was curious, you said that you can use neutrinos to understand kind of the oscillations and the detections of like the SASE and the phase transition. But is there a way it could also be used to learn more information about the high frequency feature? I'm not exactly sure, but since the frequency of the gravitational waves goes up, I imagine that maybe the flux of the neutrinos coming from the protoneutron star could also be detected, because that's when the electrons and protons that are like residuals are combining together or something. At least that's what I think happens.
Yeah, sure. So in principle, the idea from that kind of the SASE meter or PT meter can be used to analyze the oscillation behavior at any frequencies. So because anyway, we are just creating such kind of the statistical tool to analyze the possibility of the oscillation, but we do not need to specify what is the frequency of that oscillation, because that naturally comes out from our parameter estimation. So, but if the frequency is extremely high, that could be a problem. Because if we have a very high frequency behavior, then we need the neutrino time beams to be very short. Because the high frequency means that you need the time resolution to be extremely high. But if you have a very short if you have a very small neutrino time beam, then the neutrino events collected in those beams will also be correspondingly smaller. If you have a smaller number of the neutrino events in those very tiny neutrino time beams, then you have to suffer a larger statistical fluctuations, and which means that the noise is higher. So basically speaking, yes, in principle, you can to analyze any frequency that may probably occur. But when the frequency is too high, you may suffer a noise problem. So that's the answer. Yeah.
Thank you. Is there any other question? Okay. Oh, one more here. Then probably we will close the session after.
Thank you for the presentation, Zidu. Can you
Oh,
please switch back to the slide where you explain the toy models that you have been using?
yeah. Here or here.
Is it off? Yeah, I don't think Zido can hear if the microphone is off.
Hello. Sorry, I cannot
One
hear
second,
you.
we are giving him a different microphone.
Okay.
This one works.
Yeah, the previous slide, just the toy models. Yeah. So it seems to me at least a bit counterintuitive that the heavier progenitor actually the shock is revived and you see supernova, while the lower mass goes into a black hole formation. So is it is my intuition wrong, or are there other factors that you haven't explicitly mentioned?
Yeah, so I took those models from Adam and David's simulation. And at least as far as I understand, this type of the very, very obvious difference between explosion and non-explosion is due to the structure of that progenitor star. It's due to some kind of the silicon burning layer in that progenitor. Although the progenitor mass is about the same, but the structure could be very different. So, David, please correct me. But because I mean, the best person to answer this question is David, because he's the guy making these models.
Okay, thank
thank
you
you.
so much.
Thanks, Sidu.
So I think we can close the session. If you have a question, you can talk with it. Let's thank Zidu again.
Thank you, everyone.
So yeah, this closes the section. As we said, we don't have talks this afternoon, but I assume, Marek, are you going to say a few words about the